No, not at all. So I'm sitting here in the chair with the iPad. I don't want to stand up the whole time. I ate breakfast and I feel like can't say the next word. What's up? Have I what? Are we going to start it? Is that what you said? No, not today. Probably next week. Thanks. I didn't shower, so my hair's a little messed up. So I did yesterday, but not today. So that's why I have the head on. I really don't want to go to my next two classes, but I got to turn in homework for one of them. That's my late one too, 1:30. All right, so last time we started talking about this, right? And then we gave the formula for the test statistic for a t-test. And it was, nope, not that, there we go. The t-test statistic was found by x1 bar minus x2 bar minus mu1 minus mu2 divided by its corresponding standard deviation, which was S1 squared over N1 plus S2 squared over N2. So it was the same idea that we had whenever we're doing a z-test. It's just in this case, we don't know sigma 1 and sigma 2. So we use estimates S1 and S2. Everyone okay with that? Then how does that simplify? Yeah, so this goes away. So you're just left with x1 bar minus x2 bar divided by that standard deviation. Just like we said last section or last time, this we can think of as the point estimate. And this here, the standard error. Then using that, you can create a confidence interval using that idea. You have the point estimate, x1 bar minus x2 bar plus or minus, and since we don't know sigma 1 and sigma 2, we have a critical t value times the corresponding standard error. Can everyone read what I'm writing? Great. Yes. So you have S1 squared over N1 plus S2 squared over N2. Then I think that's where we stopped. Yeah, so note the degrees of formula changes here, and y'all got scared. And the formula I gave you, which was very awful, is called Satterthwaite's approximation. And we're not going to use that. So don't worry about it. N2 minus 1, yes, correct. So where did that come from? Yeah. So our textbook use the smaller between N1 minus 1 and N2 minus 1. And that'll be the degrees of freedom used to find the critical values.
I remember you said you need to know the name of the complex.
Not really. It's called Satterthwaite, but I'm not really going to test you on it. They put it in our curriculum for the class to teach, but I guess I mentioned it because that's how your calculator uses it to find degrees of freedom for a 2-sample test. That's why I said you can't use the calculator to do this part, because it'll give you a different answer. Then let's look at this example here. We didn't go over this, did we? Okay, cool. Okay, it says a researcher wishes to see if the average weight of newborn male infants, should say, oh, I still haven't changed that. It says are different, it should says is different from the average weight of newborn female infants. She selects a random sample of 10 male infants and finds their mean weight is 123 ounces with a standard deviation of 8 ounces. She selects a random sample of 8 female infants and finds that the mean weight is 116 ounces with a standard deviation of 5 ounces. Can it be concluded at the 5% significance level that the mean weight of the males is different from that of the females? Assume the variables are normally distributed and the population standard deviations are not equal. Okay, so you can either say group 1 corresponds to the males. Group 2 corresponds to the females. And then using that, we have the null hypothesis is what? Assuming the two of them are equal. So assuming the mean weight for males and females is equal. So mu1 minus mu2 equals 0. Or you can write it as mu1 equals mu2. The way I have it in your completed notes, it's mu m minus mu f. So m for male, f for female. It doesn't make a difference. Then, what is the alternative? Yeah, they're not equal. Right here, the last part it says is different. We don't know whether it's going to be greater than or less than for the male infant weight. So it'll be mu1 minus mu2 does not equal 0. Or another way you could write that as mu1 does not equal mu2. Everyone understand that first part? Now into part 2. Find the critical values and state your decision rule. Now, so this is a two-tailed test, right? The alternative is not equals. Then the first thing we need to find is what that we're going to use to find the critical value. Yeah, you need to find the degrees of freedom. So you need to look at the smaller between n1 minus 1 and n2 minus 1. So what is n1 minus 1? N1 minus 1 is 10 minus 1 or 9. What is N2 minus 1? Yeah, so it's 8 minus 1 or 7. Which one's the smaller between those? 7, obviously. So then we use the degrees of freedom as 7 for this. Then what you're going to do is look at your t-distribution table. For alpha is 5% or 0.05. You're going to look at two tails, and then you're going to intersect that with 7 degrees of freedom and tell me what you get. You'll take the positive and the negative of that number since it's a two-tailed test. So you have some positive and negative. T alpha over 2 is equal to positive and negative what? Yeah, 2.365. Then since it's a two-tailed test, the rejection region is going to be on what? One side of the z distribution or both sides? Both. You'll have two tails. And what is the decision rule for it? Yeah, so reject the null hypothesis if the absolute value of our t-test statistic we compute is greater than the critical value, the positive critical value, so that would be greater than 2.365. So your homework won't ask for part 2. I just write it out. That way you know how to determine what you're going to do. As far as your decision is. Holy cow, there's no one here today. Then the next part, compute the test statistic and the corresponding p-value. Don't worry about the p-value, it's a t-test. Then, remember that little table we made last time? X1 bar, N1, and S1, X2 bar, N2, and S2. X1 bar is the mean weight for the males, and what was that? Yeah, 123 ounces. And their sample size for the male infants is what? 10. And the standard deviation for them was what? Yeah, 8. What was X2 bars? So the mean weight for the female infants? 116. N2, so the number of female infants sampled was what? 8. That is an ugly 8. And what was the sample standard deviation for the female infants? 5. Then plugging that into the test statistic formula, you have t-test is equal to x1 bar minus x2 bar divided by the square root of S1 squared over N1 plus S2 squared over N2. So just plug all those in. In the numerator, you have 123 minus 116 divided by, so it's asking for S1 squared, so that would be 8 squared divided by 10, because N1 is 10, plus 5 squared divided by 8. Now someone tell me what you get to 2 decimal places. Yeah, correct. 2.27. Everyone online, are you following what I'm doing? Okay, great. Then reach conclusion and make an interpretation. Now, since this here, so the absolute value of 2.27 is what? It's just 2.27. And is 2.27 greater than 2.365? No. So you fail to reject. Fail to reject null hypothesis. So there is not enough evidence to conclude the mean weight of the males is different from that. Just say is different than the females. And that's the conclusion. Does everyone understand how I did that? Now we're on to 9.3. So this is the section I said I was going to throw out if we didn't have time, but we have time. But I'm not going to test you over it. That's not on the homework. This is where your bonus opportunity will come from, though. I put a question up on Canvas. I just posted it like 5 minutes ago. There's one problem that I pulled, and it's up to 5 bonus points, and it will be graded on correctness. You have until Sunday to submit it. So I'll show you how to solve it. Now, last section, the 2 samples we had were independent of one another. So this section, what happens if they're dependent? Then you do a t-test. But what we're going to do is look at the difference between each pair. It's called matched pairs is what it's called. So it says, say we wish to study the progress of students' grades in a specific statistics class. We could take a random sample of students taking the course and report their first exam grade and the final exam grade. We can then run a t-test to determine if there was any improvement. So what the setup would look like is something like this. So here at the top, you have, say, students, and you have their first exam grade here, and their second here. And then we have this for so many students. Say we have for student 1, 2, 3, 4, and so on. And then for each of these students, we're going to take their first exam grade, record it, and their second exam grade and record it. So for instance, for the first one, say they got an 82 on the first exam and a 93 on the second. We're going to call this X1. We're going to call the second exam X2. What we're going to look at in this section is running a single 1 sample hypothesis test on this, the difference X1 minus X2. So what it will look like then is we're going to take the first exam score minus the second. So that gives you minus 11. And say the next one, they got a 90 and I got an 80 here. Then that difference would be 10. 90 minus 80 is 10. And we do that for every student in the class. And now, since exams are dependent on the student, so the exam score depends on which student is taking it. We will test the mean of the differences. And we will denote that difference mu with the subscript d for difference. And like I mentioned a second ago, this is known as a matched pairs t-test, or you can say a paired t-test. Then it has some assumptions that must be made since you're doing a t-test. So obviously you don't know the 2 population standard deviations, or you would do a z-test. The samples are random. The next one, the populations are normally distributed or their sample sizes are each greater than 30. And then what is this last one, do you think? The samples are what of each other? Dependent in this case, since we're doing a dependent sample test, dependent. Now here's another one of the tables. Don't worry about it. It's the same thing as it's been all the time. Then it says, what is mu d? So mu is the expected value, right? So if we're looking at the expected value of the differences, it will be the expected mean of the differences of the pairs. And we will denote d as x1 minus x2. And mu d is just mu1 minus mu2. So instead of treating it as two different samples and then looking at the difference between them, we're treating it as one. And we're just running a one sample t-test on the column of differences. And we're seeing whether or not that expected mean is going to be equal to 0 versus the alternative. And the test statistic formula can be found by this. So t-test is equal to d bar. What do you think that is? So if b represents the difference for each of them, d bar represents the mean difference for the whole sample, minus mu d divided by SD. SD over the square root of n. But under the null hypothesis above, we have that mu d equals 0, so this part goes away. You're just left with d bar divided by SD over the square root of n. And d bar is equal to the sum of all the differences divided by the total number of differences you have, n. And then SD, this one's not fun. It will be n times the sum of the differences squared minus the sum of the differences, that quantity squared, divided by n times n minus 1. I don't think you want to compute that. What do you think is the easiest way to find d bar and SD? So you can either use your calculator or you can use Excel. You want me to show you how to do it? Okay. Let me stop sharing on this and I'll start sharing back on here. Okay. Stop the broadcast. Share screen. And we'll go. All right, so let's look at the example that's in your notes in a second. Whereas, please tell me they have Excel on this computer. Good. Then there's also a confidence interval formula, but I didn't go over it yet. All right, so on the next page, it gives you all this stuff. And then it'll tell you how to calculate D and SD at the bottom of page, whatever that is, I don't know. Use your calculator, it says. The first thing, enter the differences into the calculator and then run one variable statistics on it. Another way you could do it is doing it by this. So in this first column here, this is the example where it says a dietitian wishes to see if a person's cholesterol level will change. Then in the first column here, we're going to put the before 235, 208, 190, 172, and 244. Then in the second column, put the after scores for each person. So for the one with 210, their after score was 190, then 170, 210, 188, 173, and 228. Then once you have that entered in, go into the third column here, hit enters, this before score minus the after score. If you do that for one of these, then to do it for all of them, you just drag that down. And it uses that same exact formula format to do all of them. See, it takes A2, this one, minus B2, then A3 minus B3. So this column here is your differences. Then you want to find the mean, so D bar, so equals average, AVERAGE, and select the cells you want it to take the average of. So you want it to take the average of those cells. Close the parentheses and hit enter. That tells you D bar. Now to find SD, the sample standard deviation, go one more down, equals STDEV, and then put a dot, and then tell it whether it's S or P, so whether it's a sample or a population. In this case, you have a sample, so hit S, open the parentheses, select the cell you want it to take the standard deviation of, close it, and it tells you the standard deviation. So this here is mu D, and this is S. And that's the easiest way to find them. The mu D equals average. And then select the cells you want it to take the average of. So this differences cells. And then SD was take the standard deviation dot S of the cells you want to take the standard deviation of. Is that a little bit easier? You want me to show you how to do it on the calculator too? Okay. So let's keep this in mind. Mu D was 16.67 and SD was 25.4, basically. So hit stop share. I'm gonna turn this on and share this over here in a second. Yeah, let's see, is it on now? No, can't see it yet. And I'm on. Then First thing you want to do is make sure you don't have anything in your list. So go to stat edit and make sure the list in there are empty. If they aren't, do you know how to clear them? All you do is hit stat, clear list, and then the number of the list it is. Then just like we did in Excel, in the first column, put the before score. So it'd be 210, 235, 208, 190, 172, and 244. So those are the before scores, and then in the next column, put the afters. So you'd have 190, 170, 210, 188, 173, and 228. Everyone with me up to there? Then in the third column, so where it has this first thing right here, where it has those dashes, go up into the top where it says equals L3, or just says L3, hit enter. Then hit second L1 or second one, that'll take the first list. And then minus second L2. So it's going to take each individual entry in each of those and subtract them. Then to run that, just hit enter. And it takes the differences between those. Everyone okay with that so far? Then once you have this column of differences, you're going to run one variable statistics on this column of differences. So that's on the third column. So hit second mode. That'll just take you back to the home screen. Then go stat, calculate, one variable statistics, tell it the list. So in this case, it's in the third column. So hit second 3. Then where it says freak list, don't worry about that. Just go to calculate. And look, we get the same thing. 16.67 and 25.39. Or 25.4 is how I rounded it. What's up? L4, you hit second and then 4. So just hit second and the number of the list it's in. Everyone okay with that? You want to see the longer way that your textbook shows you how to do it, and you get the same exact thing? Here's how I did it. Here's another way. Here is the corresponding X1, so the before scores, here's the after. Here's the difference, and here's the differences squared. So then I have the sum of the D's and the sum of the D squareds like I need for the formula. So I can find D bar by taking the sum of the D's divided by the total number of differences I had, which is 6. And look, you get the same thing for D bar, 16.67. Then SD, you just use these two right here and N. So N times the sum of the differences squared, which is 4,890, and minus the sum of the differences, that quantity squared, which is 100 squared. Then divide that by N times N minus 1. And look, you get the same thing. It's a lot easier way to do it on your calculator and Excel than doing it by hand. Last semester, I put this on an exam, but I did not make them do this. I gave them what the sum of the D's and the sum of the D's squareds were. So you had everything you needed to find SD and D bar and then run the hypothesis test. Then, using that information that we have, you can run the hypothesis test. So let me go back to sharing the screen on my iPad. There we go. So then go back here. Okay. So now the first part. State the null and the alternative hypothesis. So we're testing whether the mean difference is equal to what or not. We're testing whether mu d is equal to 0. So the before and after scores are the same. Versus what? Yeah, not equal to 0 because I don't tell you whether it's greater than or less than. Mu d does not equal 0. Then it says find the critical values and state your decision rule. What kind of critical value is it going to be, a z or a t? What was it? Yeah, it'll be a t because you're computing the sample standard deviation. So you're going to find a critical t value. So you need the degrees of freedom. And what would be the degrees of freedom in this case? Yeah, you have 6 pairs and then -1, so 5. Then intersect 5 degrees of freedom with a two-tailed alpha of what is it, 0.1, and tell me what you get. So positive and negative t alpha over 2 is positive and negative what? Yes, correct. 2.015. Then stating your decision rule, since it's a two-tailed test, again, you're going to have 2 rejection regions. So the easiest way to state this is reject the null hypothesis if the absolute value of your t-test statistic you compute is greater than the positive critical value of 2.015. That makes sense to everyone so far? Then part 3. So this is where you're gonna have to compute the test statistics. So you need to know D bar and SD. So D bar was what? We'll just round to 1 decimal place. So it was 16.7. And SD was what? Yeah, 25.4. And N is equal to 6. Then using the formula, we have the test statistic t-test is equal to mu d, or not mu d, d bar. D bar divided by SD over the square root of N. So just plug them in. D bar is 16.7. SD is 25.4. And N is 6. Someone besides Randall, tell me what you get. So 2 decimal places. Yes, correct. So it says find the corresponding p-value. I don't really expect you to do that. Do you want me to show you how to do it or not? Okay, great. It's on the calculator. We usually show you how to find like a range of p-values, but that's not on your homework anymore, so. Part 4, reach conclusion and make an interpretation. What is your conclusion based on this t-test statistic and comparing it to the critical values? Yeah, so fail to reject the null hypothesis. So fail to reject the null hypothesis because this t-test you computed 1.61. The absolute value of that is again 1.61, and that is not greater than 2.015. So you fail to reject the null hypothesis, and the interpretation is there is not enough evidence to conclude the cholesterol level change. That is it. Do y'all want to work on the bonus problem in class? Okay, y'all can talk together with your people about it. I'm going to show you what it is. So let me stop sharing it on my iPad real quick. I'll share the screen on this. Okay, the bonus question should be posted under assignments and go down to chapter 9 bonus. And then it's right there. Okay, so this one is basically the same kind of thing. So it says for a maximum of 5 bonus points, do the following problem, and it's graded on how correct you are. A random sample of 9 local banks shows their deposits in billions of dollars 3 years ago and their deposits in billions of dollars today. At alpha is 0.05, can it be concluded that the average in deposits for the banks today is greater than it was 3 years ago? So which one in this case is going to be X1 and which is going to be X2? Yeah, X1 is 3 years ago and X2 is today. Would it matter if you switched those? It would affect the alternative, yes, but overall it would give you the same decision. It would just be, instead of like the positive test statistic, you'd get the negative of it. And instead of the positive critical value, it'd be a negative critical value. All right, so the idea here that we had is basically the same. Identify the null and the alternative, find the critical values and state your decision rule, compute the test statistic, and then make a decision. So I'll let y'all work on that. People online, you can work on it too. Where the heck is it? There it is. All right. So for the alternative, it's not what you think it is. That's why I took it out of your homework. Because you're thinking that if it's greater than, the alternative is going to be the difference is greater than 0. Let me turn myself around. This and this. Okay. So your null hypothesis, most of you got that right. Just the mean difference is equal to 0. The alternative, I don't think anyone got it right. It's less than yes. So we're saying that, say, mu d is equal to mu1 minus mu2, right? Oop, not equals mu2, minus mu2. Mu1 is going to represent the population mean deposits for 3 years ago, and this will be today. So this is 3 years ago, 3 years ago, and this is today. We are saying that the deposits are going to be greater today than what they were 3 years ago. So that means this number here is going to be smaller than this one here. So when I take the mean difference, it'll be less than 0, or you can write that as mu d less than 0, or mu1 minus mu2 is less than 0. I'd write this one though. Does everyone understand why that is? Because on your homework, it used to have an example where it says you practice playing some instrument for a little bit, and they hypothesize that the mean number of mistakes you make playing a song is going to go down. So that means in this case, the number of mistakes would be, or after would be mu2. And in that case, if you made less mistakes, then this difference would be positive. Does everyone understand why that is that way? What's up? I will come. I am heading that way. Turn the video back off and my volume off. All right. So are there any questions over this before I let y'all go? All right. How's what? I see. Correct.
I'm making my way.
Yeah. Then compare that to the rejection rule. So you reject the null hypothesis if your t-test is less than negative 1.86. Yes, correct. Mhm. If anyone has your textbook, that's a straight example from your textbook.